Today I will say a few words about another type of dark matter, so which is still part of the problematics of the hidden part of the universe. Yeah. Okay. Which is the dark matter under the shape of compact objects that may be baryons or something else, but basically probably most probably baryons. So I would say a few words about the way we can constrain the galactic structure from the microlensing. So the technique that will be used here is the microlensing. The initial motivation of the microlensing surveys, the very initial motivation was really to search for the contribution of the compact objects to the galactic halo. And is there a laser here? Yeah, well, very weak. Okay, anyway, so at the time these surveys were initiated, the main question was, and it's still an active question, was the composition of the galactic dark halo in terms of baryonic objects. So the microlensing survey started with monitoring of the marginal clouds, which are just out of the galactic halo, just at the border at the limit of the galactic halo, and with the intent of probing the directions, the line of sight between the sun and the galactic halo, and the magnetic clouds just crossing the largest possible fraction of the galactic halo. So the microlensing, this is this is a sketch of the microlensing event. So in the case where a massive compact object, that's to be compact because the Einstein radius has to be larger than the matter radius, just to avoid to have, if the matter radius is larger, then you have an eclipse rather than microlensing. So if the Einstein radius, so if an object goes close enough to the line of sight of a remote point-like luminous source, then the observer receives two images instead of one direct image, and but the angular separation between the two images for the microlensing is extremely small. It's of the order of microhexagons. So it cannot be detected so far. It has not really been detected so far. But the observer receives temporarily more light from the source than it should come from the direct, undeflected line of sight. So, so the parameters, the main parameters here are the Einstein ring, the Einstein radius, which is given by this formula, and the transverse speed, and then this transverse speed is such that during the time the magnification, the status of the magnification of the background object varies with the time. So here you have description of a microlensing event. So you have. So this is now represented in the transverse plane, projected transverse plane. You have the deflector, and you can either consider that the deflector goes in front of the star, or the star goes in the background of the deflector. So you have this relative velocity between the source star and the deflector. This is the minimum impact parameter, and this minimum impact parameter is correlated with the maximum magnification you expect from the magnification, that's a magnification. So this is what you will see in your telescope, assuming that you have the same conditions, same observation conditions, and this is the light curve you observe. So which is this is the flux versus time. So when you enter the Einstein ring, so this is called the Einstein ring with the Einstein radius here. As soon as you enter the Einstein ring, the magnification is larger than 1.34. Well, it's a type of a magic number. So it corresponds to an reduced impact parameter, reduced in terms of U0 divided by RE, which is 1. And you can reach sometimes very strong magnifications up to a few hundred times. A few hundred magnifications have been observed in a special case of microlensing. So the characteristics of the light curves are the symmetry with respect to the time of maximum magnification, achromaticity. If your deflector is a pure source with no blending with other stars, then you expect something. You expect a light curve which has to be achromatic, so the same as should not depend on the wavelength, the shape. And it's also, you can say that with respect to the lifetime of a survey, you can say that this star should experience such an exceptional event only once in the lifetime of the light curve. If you see several bumps in the lifetime of the survey, it's probably the indication that you have something else than the microlensing.
Why?
Sorry?
Why is the last the unique? I mean, in principle,
Yeah, because of the very small probability for a star to lie behind the lens. You have typically it's typically the probability for a given star to be lensed by a factor of more than 1.34 is of the order of 10 to the minus 6. So if you want to have two events in the lifetime, it's just a product, the square of this term. Except if you have correlated multiple lenses, but this is a different case. Which
is the probability that a star is lensed by another star in the Milky Way, or?
Yeah, but this probability is of the order of 10 to the minus 6.
So now you're going to move to dark matter at some point.
Yeah. This is general description of the microlensing. Okay, so by the way, that's the optical depth, which is the probability for a given star to be behind an Einstein disk. So this is something which is proportional to the square of the Einstein radius, which is proportional to the mass of the lens. Then the total optical depth is proportional to the sum of the mass of the lenses, which is proportional to the total mass of the probe, of the structure that you are probing between the observer and the source. Okay, so this I just show you one example of the candidates, of the really observed candidates. So this is the magnified star through microlensing, and you see here as a function of time the variation maximum and then decreasing. The variation here is related to the change of the seeing conditions, which are the observation condition. But here you have for example, this is one high signal to noise microlensing, and this is now routinely a routine microlensing event. Okay, so now I go back to the Milky Way structure. So there are several structures in the Milky Way. You have a bulge here. You have a bar with the shape which varies with the authors. You have a thin disk, a thick disk, spiral arms, which may also concentrate some mass, and you have the galactic halo, which is the most unknown part of the galaxy. So all these structures have their own density function as density. The 3D density function, and they have also different kinematics, which will give different classes of events, of microlensing events. So the main targets that have been monitored so far by the microlensing surveys are first historically the Magellanic Clouds. So to go through the halo and directly going out from the galactic plane, so you only probe the galactic halo. The Galactic Center, where you can be sensitive to all the small stars that are between the Galactic Center and the Sun. Spiral arms, which are within the galactic plane but far from the Galactic Center. And also there have been some experiments that have looked somewhere else than in the vicinity of the Milky Way, which is typically M31, where you cannot you cannot distinguish between stars, so you have to use a special technique where you are looking for pixels, and where for some places where stars appears temporarily due to microlensing as a signature of magnification of strong magnification of a star, which is not resolved in the galactic in the field. Okay, so the microlensing observables, if I assume what we call in microlensing science the simple the point source, point length, and constant transverse velocity, it's the basic, the simplest events. From these events, event by event, you can only the observable you take from one event like this is the Einstein radius crossing time, so which is the ratio between the transverse velocity and the Einstein radius, so VT divided by reverse, or the time you need to cross the Einstein radius. So this is the only observable that you get for one event. Now, if you have a series of events, you get a statistical information, like the optical depth. I have said before, it's just the probability for the stars to be behind Einstein radii. And the distribution, the Einstein radius, the Einstein duration distribution gives you also some constraints on. So you get information on the masses, degenerate information on masses, and on the kinematics of the population. Though you can extract some constraints on the initial mass function of the lenses, and also constraints on the relative kinematics between the observer, the lens, and the source. If you are lucky enough to be sensitive to what I call non-standard events, which are events that have been that are affected by, for example, parallax, which means that the transverse velocity of your deflector with respect to the line of sight is not anymore a constant velocity, because you have to take into account the rotation of the Earth around the Sun. So instead of having your source having a regular translation with respect to the background, you have a type of cycloid apparent trajectory of this object with respect to the background. Then if you have this, you have the variation of the magnification with time is more complicated. So you have some oscillation for the very long events, which last for 1 year typically. So parallax, you have also the source. The source is not really a point-like source; it's an extended source. It's a surface. It's a star. So you can, in some cases, you have to take this into account, and you have to go beyond the simple approximation. You can have multiple lenses. Well, all this gives you extra information, the distance, and then the mass velocity. Okay, so this is more or less this is the same. That has the optical depth. This is for example, a distribution of the Einstein duration for the events, and this gives you can compare this with the modelization and see if it agrees with the standard model of the galaxies. So in the Galactic Center, all the surveys, so Eros, Macho, Ogle, and Moa, have observed thousands of events in this direction. So there is a bright and past and a bright future for this. This is mainly studied by the people who are looking for exoplanets. There is a very strong community working on this. Towards the galactic arms, if you go farther from the Galactic Center, there is, to my knowledge, there is only Eros. That's the only collaboration that has monitored the microlensing in these directions with only 27 events, which is not bad, because you can have some direct information on the distribution of mass in the galactic plane. And so there is a serious potential there because, okay, you can, if you can be free from extinction, if you are looking in infrared in these directions, you can say much more on these directions. And the galactic halo have been monitored by these 4 collaborations also. And if you join all the, if you join all the databases from these 4 collaborations, you have some parts of the field in the LMC and SMC that has been monitored for 27 years. And as you will see, this could give an interesting probe for the hidden matter made of very heavy baryon objects. So then for heavy black holes, which is now there's a revival interest for this type of objects. So this is the status of the surveys toward the Large Magellanic Cloud. You have to read this plot as follows. In this direction, you see the maximum contribution to the galactic halo in fraction, so 10%, 20%, so on. And this is, if you look for the objects at a given mass, for example, 10 to the minus 2 solar mass, you can read from this plot that the maximum contribution of the object with 10 to the minus 2 mass to the Milky Way halo is less than, well, I would say 2% here. So then you can generalize this plot. For example, you can read as follow. You can say that between 10, all the objects with a mass between 10 to the minus 7 solar mass to about 10 times the solar mass cannot contribute for more than 20% of the galactic halo. So it is essential to put these limits as low as possible and as far as possible if you want to probe for the black holes. Now you have also, just to give you an idea, if you assume that all the halo is made of objects of 0.4 solar masses, you would have expected about 80 events with this typical duration, and we saw none. So there is basically no events. Well, there are 2 events, but they are due to what people call the self-lensing. I will not go into the details, only if there are questions on this. So, I have a proposal to search for to search for very long events, because if we want to have a good sensitivity for the heavy events, we have to go to very long timescale events. So we have to benefit from the maximum duration and try to join all the database from the different surveys. So I call this MEMO, Moa-Eros-Machogol. It's a combination between all the surveys. So that's to have a much better efficiency for search for large events, large duration events. So we made a very simple, a very reasonable hypothesis, which is for extrapolating the efficiency. All right. One of the important points here is the control the efficiency. If you want really to make a quantitative result regarding the galactic structure. And the very basic assumption we did is that the efficiency depends on the time, on the duration of event, on the time of the event, the time of the maximum, and on the sample. And if you just decide to multiply by a given factor all your times, you have the same light curve. If I change here from days to hours, I will have in my analysis, I will have exactly the same efficiency. But the idea is that I say that if I multiply this by 10, I will have the same efficiency with the same sampling, but in reality I will have a better sampling. So I can infer that we'll have a better efficiency so then by using this equality, I will be pessimistic in the final number, in the final sensitivity to a combined analysis of the light curves. So we did the exercise by just simulating the combination. It's not real combination, it's just a projection of what we could expect if we do this analysis, combined analysis. And as you can see, we can go much farther here. If you combine here, you have Eros only, you have Ogle 3 only, which are the best limits so far. And then if you combine the database, because you will be able to have a strong sensitivity due to the fact that you have much longer light curves, you can go up to almost 100 solar masses sensitivity to search for the heavy dark holes, so heavy black holes. So that's clear that this is the main motivation. That's the recent gravitational wave signal. And so maybe the question is the dark matter just behind the corner, just behind what have been already published by the Microlensing surveys. Okay, so very briefly, as a conclusion, I just show you that the other directions toward the galactic center of spiral arms, they all okay. So this is the optical depth as a function of the galactic latitude here, and this is the various surveys which are compared with a few models. And the most updated, I would say, model is the Besançon model, which is a model of the distribution on the mass distribution, density distribution within in the Milky Way. And there is a good, fair agreement between these results and what is expected from the Besançon model, without assuming hidden mass in the galactic center. Now, if you add the spiral arms measurements, which are far from the galactic center, here, 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 and here, so you also find optical depth here, which are measured here. If you compare to the optical depth expected from the Besançon model, you see also that there is a fair agreement, and there is again no need for adding hidden compact objects within the galactic thick disk. All right, so my conclusions now. The microlensing is one of the best tools. I think that microlensing is one of the best tools to search for black holes in the galactic halo, maybe in the plane, but probably most probably in the halo. And from the galactic plane microlensing, we see that there is no need for hidden compact objects. This is about the fine structure of the galaxy. The inclination of the bar has been confirmed. The initial mass function also, we have some sensitivity to the initial mass function. And but I think that the most important is for the conclusion is this, and the fact that there is no need for hidden compact object in the galactic plane. Well, the perspectives for the microlensing, so there is first this perspective to increase the statistics by combining the existing database. So this, I hope this will be done with the help for during a PhD thesis within the next 1 or 2 years. There is the survey which is the most sensitive at the moment is the Ogle 4, which is still running, and there is in the larger horizon, this is the LSST, Large Synoptic Survey Telescope, that should also be very strong. That should also give a lot of data in any direction of the sky, and that should give us a very strong sensitivity to the microlensing, especially in the directions of the large Magellanic clouds, in view of measuring the dark matter in the galactic halo. Thank you for your attention.
Questions?
Sorry, can you go back to your plot of the extrusion plot that you had, like just 3-4 slides back? Yep. Yeah. Whatever.
This one?
Yeah. Doesn't matter. Yeah, this one is good. So, I mean, I'm wondering if, for example, this story about primordial black holes with like masses of like 30, 40 solar mass, actually.
Yep.
That would be really dark matter. I mean, these are exclusion plots. So, what would you expect to see? So, if there is a detection, what will be in this plot?
Here, expected number of events.
So,
if
for example,
this is the expected number of events, the halo is completely made of these objects.
Sure. I'm talking about the other one, the other plot. So you have it in terms of the diffraction of like the density fraction and like the mass. So there will be a detection. Imagine that there is a detection. So
yeah, here the detection would be a few events here.
Okay, and then we don't have an exclusion anymore. Right?
You will have now. That's you deduce this from this.
From this, okay.
Here, this is what you expect if you have 100% of the halo, and this is if you find. If you find zero, if you find zero event, then you have this exclusion.
Sure. So let me put it this way. So can we get a plot such a way that say, okay, we have this mass and this fraction of the matter will be actually with that mass. So there will be some kind of like a contour or something.
Yeah, absolutely.
Okay, that's what you are.
Yeah, if you find some events there, then you will have a contour instead of an exclusion. Well, yeah. Sorry, yeah, I should. The pessimistic view is to show an exclusion plot, and the optimistic view is to show a contour plot.
Yeah, maybe you mentioned, are those sources polarized, the sources that you use?
That's just stellar sources. It's stellar sources that are not polarized, but at the time, at ancient time when I was more active in this field, I remember that in some cases, if you are in the case where you have a strong magnification, then you are amplifying the different part of the star of the disk with different amplification factors. Then you could expect some residual polarization due to the polarization of the atmosphere of the star. I did some calculation long time ago, and just a few percent of but it's very marginal. It's very special cases.
But if I wanted to use polarization of this to test some stuff, you say it's not a big.
The polarization would be just due to the fact that you magnify some part of the star stronger than others. So only in cases where you have very strong magnification events and very specific events. So very rare. I don't think it has been detected up to now an effect of polarization.
More questions? If not, thanks again.